Okay, so I'm just going to go over the solution to the chapter 4 and 5 quiz. So this is going to include Newman projections and RNS configuration of stereochemistry. Okay, so to start with for Newman projection, I imagine myself standing just like right here on this side of the molecule. So if you could visualize yourself standing and looking on the molecule from this side, the bromine would be coming out of the page. So if you're standing here looking at it, I like to lean down as if I'm looking at it. That would be on the right side of you. So I draw the bromine on the right, and then the hydrogen is on the left going into the page. If it was on like the other side of my desk, it would be on the left side. So if this was the plane of the page, here's the wedge and here's the dash, right? It's going on, if you're looking from the side of my thumb, it'd be going into the page. And then anything in the plane of the page here is just going straight down. Now, sometimes students try to generalize like, oh, then if it's a wedge, it's on the right. But that's not always the case, because if you're looking from the opposite direction, the wedge would be on your left. So you have to make sure to tell where you're orienting yourself from. Oh, and this was supposed to be between 1 and 2 carbon. So that's the front carbon, and the back carbon right here has a long chain. I just usually draw the chain, so it's CH2, CH3. Sometimes people will write out CH2, CH3. Either of those is fine. And then there are 2 hydrogens here and here. And it doesn't matter if they're a wedge or a dash, because it's the same if you flip them. There's not a stereocenter there. Okay, so that's the basic conformation, but I'm supposed to be drawing the most stable, so I shouldn't have drawn this one in the box, but most stable conformation will have the 2 biggest groups opposite of each other. So the biggest group on this front carbon is the bromine. Bromine is bigger than fluorine, and the biggest group on the back carbon is a CH2CH3. So the most stable conformation will actually look like this CH2CH3 here, and a hydrogen and a hydrogen. So this is how I would draw the most stable conformation. If you want to rotate the front carbon so that the bromine is pointing down, that's totally fine. So this is the anti-conformation, and the 2 biggest groups anti to each other is always going to be the most stable, and this would be considered the gauche, which is the next most stable. So if you have that, diagram that looks like this is anti, and these positions would usually be gauche. And then the higher positions that are less stable are going to be the eclipsed. Okay, so the least stable is when the 2 biggest groups are completely eclipsing each other, or completely covering each other up. So if we start back here, I'm going to rotate the back carbon, and I'm going to move it just half a rotation to where it's right behind the CH2CH3. This hydrogen would be right behind this fluorine, and this hydrogen would be right behind. So this would be my least stable conformation. Okay, so that's the most stable. This should be the one in the box, and here's the least stable of the following molecule. Okay, next I'm going to draw the most stable conformation, so that's going to be usually the chair form of tert-butyl cyclohexane. Let's see, so 1 bromo, 2 tert-butyl, and these are cis to each other, so they're both going to be either wedges or both dashes, whatever works as long as they're the same. So if we are converting that to a wedge and dash, you would want one of them to be axial, one of them to be equatorial. If you went all around here, the ones that are all pointing up alternate axial, equatorial, axial, equatorial, axial, equatorial. So if one's axial and one's equatorial, usually if they were exactly the same, you could just pick one to be axial and one to be equatorial, and that would be fine. But in this case, we have one that's significantly bigger. Tert-butyl is huge. It's a carbon with 3 carbons around it that each have 3 hydrogens around them. So this is a really big, bulky group. So you want this group to be as stable as possible, so it's going to be in the equatorial position. And that means this bromine needs to be in the axial position. So that would be your most stable conformer. Okay. Next, we're going to be doing R or S configuration. So for this, you first label the priorities, and that's based on the Ingold, or I think whatever prelogs, the whatever prelog system. I can never remember that right, but that priority system, and that is the atom that's attached directly to the stereocenter, and whichever one of those has the highest molecular weight. So in this case, we have one bromine, one hydrogen, and two carbons directly attached. So bromine is definitely going to be higher than either of these carbons, so that's the highest priority. And then the hydrogen is going to be the lowest priority because it's definitely lower molecular weight than either carbon. But then we're comparing these two carbons. So that they start with both carbon being attached, so then you look and see what that carbon is attached to. So this carbon is attached to 3 hydrogens, while this carbon is attached to another carbon and 2 hydrogens. So this carbon that this one's attached to is a higher molecular weight. So this is the second priority and this is the third. So once you've assigned your priorities, don't look at the fourth priority. It's pointing backwards. That's correct. It's pointing backwards. So once it's pointing backwards, you can just cover it up and then connect 1, 2, and 3 together, and don't look at 4. If it's going to the right at the top, that's R configuration. If it's going to the left at the top, that's S configuration. So this is going right, so it's R. The other way you can think about this is clockwise is R, but I always get confused on what's clockwise and what's not. I don't know why. That's just hard for me. So I just look, once I've connected all of them, whatever's happening at the top, if it's right or left, that also corresponds to clockwise or counterclockwise. Because if you think of the way a clock goes, it's going right at the top, or if you're going against the way of the clock, it's going left at the top. So either one of those is an okay way to think about it. So this is R configuration. Okay, and then if we're going to draw an enantiomer of this molecule, first you have to check and make sure it's not a meso compound. So is there a plane of symmetry through the middle? No. If there was a plane of symmetry, then the mirror image of this would be identical. But in this case, it is possible to have a meso compound. So the mirror image of this molecule is an enantiomer. Oh, that should be chlorine, not hydrogen. Sorry, I drew that wrong. And then hydrogen and CH3. So this is the mirror image. And then for a diastereomer, you actually want to take the mirror image of one of the carbons. I usually take the top, just because it's easy. And then you actually want to change or invert the stereochemistry on the other one. So you can get these two to trade places, and that is going to give you a diastereomer. So instead of my hydrogen being reflected, I guess my chlorine should be there. I always get that backwards. We have our CH3 is on this side and our hydrogen's going down. There's a lot of different configurations for this that if you want to do them, but you have to reflect one stereochemistry and invert the other so that they are opposite. Yeah, that should be right. Okay, so that's everything for the problems on the describe in your own words what a meso compound is. It's something that has a plane of symmetry right through the middle. So you have to look and make sure that on both of your chiral centers, the exact same things are attached. So in this case, both of these have an alcohol, a bromine, and a CH3. And if you can draw a line through the molecule and there's a plane of symmetry, so that means there has to be an even number of chiral centers. Usually you're going to see 2. It's not usually going to have 4. That's pretty complicated. The even number of chiral centers with 4 different things attached to each one. So this has CH3, bromine, alcohol, and then this group. So that's 4 different things attached. But right through the middle is a plane of symmetry. So these are reflecting each other. And if you have that, then the mirror image of that is a meso compound. So describing that in my own words, I would say a molecule that contains chiral centers but is not a chiral molecule because it has a plane of symmetry, so that its mirror image is the identical molecule to it. However you want to think about that is fine. And I actually have with me a meso compound in case you haven't had a chance to learn about that yet. So right here we have the mirror image of this. And while normally if you have the mirror image of a chiral center, it would be an enantiomer, in this case they line up. They're identical. So you can see that this would be a meso compound. Now, if I wanted a diastereomer of this, instead of, just taking the mirror image, I would flip or swap out, however you want to think about it, invert 2 of the groups. So the bottom you can see is still a mirror image, but the top is no longer a mirror image. So this is a diastereomer. And this diastereomer does have an enantiomer. If you take the mirror image of the diastereomer and then try to line these up, they won't, because there's not a plane of symmetry in the middle here. So because of that lack of symmetry, this is not a meso compound. You have to have them exactly lined up. Another way that you can look for this is because there's a plane of symmetry through here, these are actually reflections of each other. So one is usually going to be R and the other is going to be S configuration. So a meso compound will always be RS and SR. RR and SS are not mirror images of each other, so the 2 chiral centers would be both R or both S. So if you suspect a chiral or a meso compound and you're not sure, when they have all the same things attached to them, be sure to check out to see if it's RR or SR, because they'd be reflecting it. Okay, well, I hope that was helpful for you guys, and let me know if you have any questions.